Hello, this is our demo for SkinLumina Project Group 3 for Senior Design 2025 Fall. My name is Tatiana. I'm the team lead and the Optics and Photonics Engineer.
My name is Ryan Rodriguez, and I'm also an optical engineer.
My name is Abdullah Al-Garbali, and I'm an electrical engineer.
And my name is Tiffany Tani, and I'm the computer engineer.
What you can see here are the skin samples. They're synthetic skin samples that we have created to test our device with throughout this entire process. What you can see here is our handheld base, 3D printed, and this will be the lid that covers and encloses all of the optics.
And so to get more into the lid, this piece right here is how we're exactly aligning all the optics. And to get into the optical stack, which as you can see here, basically what is going on is there's an infinity corrected lens system using two achromatic doublets, the first one being here and the second one being here in the base. And basically what that does is we're collecting reflected light from all these 30 LEDs, and that light then goes through, there's an aperture in here, and there's this polarizer with degrees of freedom, giving us 90 degrees of polarization, and then that's collected by a CMOS camera, Sony IMX219, and that allows us to capture clear and coherent images of our skin phantoms.
Beginning with the PCB is the buck converter, which translates 12 volts to 5 volts in order to power all of the system's peripherals. Underneath this plastic piece is the dev board custom Arduino board using an ATM38 mega chip, which uses RX and TX communication pins to send communication with the Raspberry Pi. Here is the stepper motor driver PCB board, which helps rotate the filter wheel and the other for multispectral imaging system. And using 6 N-channel MOSFETs is what's used to drive and power the 30 LEDs for different LED colorings. 12 volts is the beginning of the system where it translates into the buck converter itself.
Up next, we have our embedded system software live and in action. So we have the camera, which is going to capture an image, analyze the hex center code, and from there, the LEDs will adjust accordingly, and the filter wheel will move along and capture an image each and every time. All these actions are sent via UART commands from the Pi to the Arduino. We use bilateral communication. The Pi sends a command, the Arduino sends back an acknowledgement, so every LED change and every wheel movement is confirmed. So the Pi will handle the decisions, and the Arduino handles the precise real-time control. In our system, every captured image goes through a full edge and blob detection pipeline. First, the script converts the image to grayscale and runs a CLE, otherwise known as contrast limited adaptive histogram equalization enhancement to boost the local contrast. This is important because skin texture and pigmentation may vary, and we want to pull out any subtle intensity changes that indicate anomalies. Next, we combine two mathematical detection methods. The first is adaptive thresholding, which analyzes local pixel neighborhoods and creates a binary mask based on local intensity variation. From that mask, we detect contours and compute geometric properties like area, circularity, and convexivity. The second method uses OpenCV's relaxed blob detector, which fits an approximate ellipse to each bright region. And after processing, we extract key quantitative information for the UI. We compute the center hex value from the middle pixel of the image. We also output the capture resolution, the total number of detected anomalies, which we have a 85% accuracy rate, and the processing time, which is averaged to 2.9 seconds.
For this demonstration, we're going to be showing the penetration depth of NIR compared to visible, specifically blue, to show the difference when imaging in those wavelengths. We're going to be using the dermis as the base today for our sample. Each of these skin samples have different thicknesses. So this one's 0.5 millimeters, this one's 1 millimeters, and this is 1.9 millimeters. Now to demonstrate the NIR depth, we're going to stack these to a calculated depth that theoretically should image. And this is a proof of concept to ensure that our multispectral imaging system works correctly. I am getting rid of the bubbles so we can image clearly. So once these are all stacked on top of each other, it's pretty difficult for a camera to pick up abnormalities, but in NIR, we are able to clearly see certain discoloration and pigmentations. And now we're going to demonstrate how the visible light blue 470 nanometers is imaging under the same amount of thickness that NIR depth is able to penetrate. And now I'm moving it under here, and you're able to kind of see that we cannot see a single thing. So this is due to this wavelength not imaging as deep as NIR, and now we are able to use these individual samples to peel back and control how thick the skin is to really prove that these wavelengths do image at the calculated depths. So now, when I put this under, blue is able to image. So you can see very clearly.
For this segment, I'm going to be walking you through a test on spatial resolution. So basically what I have here is my SkinLumina feature analysis and detection GUI that I made in Python. And essentially what this does is it takes in parameters about the system, so pixel size, the minimum detected area, minimum circularity of the spots you're trying to detect, and it can apply different detection methods like Tiffany was mentioned, watershed, clay, open CV balance detection, and I'm also testing superpixel detection. And basically what we're going to do is we're going to go into the images, we're going to load an image, and we can zoom in on the image, and then we can apply enhancements if we want to, but what we're going to do is detect features, and as you can see it is detected regions, and then we can then analyze all, and it'll give me mean metrics for all the spots that it detected. It gives me modulation transfer function, full width, half max, circularity, and mean diameter. And what these allow me to do is estimate spatial resolution based on these statistics. And if I want to, I can even go into each blob, and it'll give me the color RGB, redness brown ratio, full width, half max again, and the transfer function. And so that's basically how we're doing spatial and feature resolution. And the smallest feature we've been able to detect is roughly 40 microns. Thank you.
This is our full semi-compact handheld system with a adjustable polarizer that a dermatologist could use between 0 and 90 degrees. And this is where a sample would go underneath, and the LEDs are pointed at 30 degrees towards the sample to illuminate it. System specification requirements that we demoed and tested with our system are highlighted in this chart. For image processing time results, this chart shows the results for the imaging processing time for each image being captured throughout the rotation. We achieved an average processing time of 2.68 seconds, comfortably meeting our system requirement specification of staying under 5 seconds. Abnormality detection rate is at an 85% accuracy, which is pretty good. For spatial and image resolution results, the analysis showed that as image blur increased, the measured full width half max values widened, while the MTF50 decreased, meaning that the image lost fine detail and sharpness. Across the entire image field, resolution stayed consistent from the center to the edges, showing that the optical system maintained accurate focus, alignment, and minimal distortion during imaging. Our target average value range was about 10 to 20 microns. Our captured average value was around 45 microns, and the smallest feature size we measured was about 40 microns. For wavelength penetration depth results, the calculated penetration depths for each wavelength through the skin phantom layers that we made were validated using our imaging system. Experimental measurements showed only an 8.8% difference from the predicted values of penetration depth each wavelength achieves, confirming that the NIR wavelengths effectively reveals features when imaging deeper than 5 millimeters. Thank you for supporting Group 3 SkinLumina.